Hey everybody, this is video for 10.6, deals with circles and arcs. An arc is a part of the circle, so you're going to have points on the circle, like D and B here. They create an arc on the circle, okay? And that arc is also going to have a relationship with a central angle. So we kind of defined central angles back when we were doing polygons. And a polygon was really circumscribed or inscribed in a circle. So central angles are part of what a circle is too. Okay. So I got a bunch of definitions here. They're asking us to do a bunch of stuff, but we don't really have a spot here to do definitions. So I wrote the definitions in the question basically they're asking. And then over here on the right hand side, we'll go ahead and kind of name or give the answers to those. Okay, so why don't you pause it and go ahead and write down those definitions, and then come on back and we'll do the answers. Okay. If you remember back with polygons, a central angle is drawn from a center point of the polygon, or in this case, a circle. They were the same thing. We're able to get an angle that's drawn from there. So C has to be the vertex. So one angle could be ACB. So angle ACB. Remember, C has to be in the middle because it's the vertex. And then I could also have an angle that's DCB. Okay. So those are central angles. All right. Another definition we have is a major arc. A major arc is that part of the circle that's going to be bigger than 180. So it's going to go more than what a diameter of the circle is. And the diameter would be 180. And also for arcs, we have a symbol. We're going to put the letters of the arc, so like the endpoints on the circle, that would define which way we need to go around the circle, and then kind of helps us understand how big they are. So major arc is going to be bigger than 180, and we're going to use this little kind of arc symbol over the letters. With major arcs, you need 3 points. So a major arc is going to be bigger than 180, and so if you look at this one, A to D is 180, so A to D to B is going to be bigger than 180. So that major arc is A, D, B, and it just kind of helps me to go around the circle in a particular direction. It helps me to understand what you need me to do there, okay? So that's a major arc, and there's a couple that we could have had there. A minor arc is going to be an arc that's going to be less than 180, okay? We're still going to use the symbol, little arc. One arc that we could use is kind of what I showed you a little bit ago. DB is a minor arc. And I only have 2 points there, and that kind of clues me in that, hey, this is going to be less than 180. And it kind of shows me which way to go. Okay, so I kind of had endpoints. They want me to name 2, so another one would be from A to B. So another minor arc is A to B. That just two points basically tell me that's going to be less than 180, and kind of gives me the direction that I need to kind of follow. Okay. An arc that equals 180 is also called a semicircle. But a semicircle is really based on a diameter. A diameter has to go through the center of a circle. So in this case, I could name it A, D. I could also call it arc A, B, D. So you don't have to really have 2. You don't really have to have 3. You just have to be able to show that that's part of a diameter and equals 180 degrees. Another kind of point we need to have here is that when we have an angle like DCB, okay, that creates the arc out here. And the central angle is going to have a certain measure, and the arc is going to be the same measure. So if you have your arcs being drawn that are kind of like intersecting an angle, or the angles intersecting the circle at 2 points, you're going to get a measure of the angle, and the angle is going to have the same measure as the arc that it intercepts. It kind of shows it down here in the box a little bit, but I still don't like it. It's not very clear. Okay, so we'll kind of show that as we go through here. Okay, I don't know if on your note packet, I didn't really check your note packet. I'm kind of using an old one. We have two angles that are given to us in the picture here, so you might want to write them in if they're not there. Okay, so once again, kind of going back, if I have an angle, so angle RAS, it intercepts and creates the arc RS. If the angle is 60 degrees, then the arc that it intercepts is also going to be the same measure. So in part B, this would be 60 degrees. Okay. You know, the other thing too we got to remember is that this is always 360 degrees. So if we use that, things have to kind of add up, or we could subtract from it. We kind of want to be thinking that way too. Okay. If we're looking at this angle here, 40 degrees, it's a central angle, but it intercepts the circle at PQ. PQ would also have a measure of 40 degrees. Okay. So it's not asking for that. So let's kind of go around here. From P to R is this. If I connect those 2 points, that draws me through the center of the circle. So therefore, it becomes a semicircle, where PR is known as the diameter. That would be 180 degrees. Okay. If I look at P to R to Q, okay, the P to R to Q kind of gives me the direction to go around the circle. The only part of the circle that arc is not intercepting is between P and Q, and we saw that was 40. So if I went, the circle's 360 degrees, and I subtracted that 40 degrees that wasn't part of the arc, I would end up with 320 degrees. So that's what PRQ is going to be. Okay. If I go from P to Q to R, so once again, they gave me 3 letters, I just follow the order. That brings me back to, once again, having a diameter. So a diameter, we're going to always understand, creates a semicircle, and that's always 180 degrees. Okay. So central angles and the intercepted arcs are going to be equal. We just kind of have to remember that a circle is 360 and kind of use that for, you know, adding or subtracting things together. Okay. All right. We go to the next page here. We have a circumference of a circle. We have a little formula for it. It's 2 pi r. R stands for radius. And for our purposes, just so that we're doing kind of things every same way, we're going to know that pi is going to be 3.14. Okay. We also have the letter D, which is diameter. Okay. When I was a kid doing this, we didn't really use 2 pi r. We used diameter times pi, or pi times diameter. That's how we got circumference. Okay. And we've talked about this before, but I'll go back over it. Circumference is like the perimeter of a circle. Okay, it's the outside line. How long is that line? Okay. The number pi here in this question is pi is irrational. What does that mean? Well, remember, irrational would be something that you get a decimal and it repeats. And so we've kind of seen this one before. It just keeps on going. So I could rewrite it as 0.13 repeating, and I could put the line over the 3. That just says it repeats. That's irrational. Well, pi doesn't repeat itself, but they have never found the end to it. It keeps calculating itself out. It hasn't repeated itself, so they determine that it's irrational. Okay, so just kind of a trivia thing there. Then we had this question about how can you use the identity of similarity transformations to prove that all circles are similar. Well, one of the things that I hope that I can explain it is that the circumference of a circle is always going to be, circumference is always going to be 2 times pi times r, or I learned it as circumference equals diameter times pi. And if I get pi by itself here, divide both sides by 2r, sorry. I'm going to get pi is equal to circumference over 2r. If I divide both sides by d, I get pi equals circumference over diameter. In most math books, they show that there's a relationship between the circumference and the diameter. And if you go back here, 2 times the radius is actually equal to d. So you kind of use in books that kind of use that, hey, there's a relationship between the length of a diameter and the circumference of its circle. So that's what gives similarity to a picture, okay? So if you had 2 circles, one was bigger than the other, you can still show that the circumference and diameter have a relationship with pi, okay? I'm not sure that we really need to worry about that too much right now for that, okay? So now we have trying to find the length of a particular arc. So in this box between A and B, that's an arc. It's intercepted by that angle. But I just want to find the length of that circle, or that arc of the circle. And so kind of going back to, with similarity between circles, I would have a relationship between this piece, this arc that I want to know, and the rest of the circle. So we have this little formula. I want to find the length of AB, and that has kind of a similarity between the measure of the angle, or the arc, because they're going to be the same, over 360, and I'm going to multiply it by the circumference, that's C, of the circle, okay? So let's kind of practice that a little bit. I want to find arc AB. I am told that the measure of arc AB is going to be 36, because these are going to be the same, because it's going from the center of the circle. So 36 over 360 times 2 times pi, so I'm going to make it 3.14, times the radius. So in this case, they told me the radius is 5. Remember, the radius is gone from the center to a point on the circle, okay? Now, just because I'm an old guy, we were taught just to kind of reduce this 36 over 360 in this case into a fraction, okay? If you want to change it to a decimal, perfectly fine, but remember it's 36 divided by 360, so you should get a decimal answer, okay? Times 2 times pi times 5, that's going to get me 31.4, and then I'm going to multiply that, and I should get that the length of AB is actually 3.14, okay? And they did give me a unit measure, so it's in centimeters. I'm not finding area, so it's not going to be squared, it's just that long, okay? All right, for the second question, EF, they want to get the measure of that arc. Well, they gave you the measure out here. It's the same thing in here, okay? So that's the central angle. It intercepts the circle right here at EF, creates an arc. The arc and the angle have the same measure, so I'm going to go ahead and use 100. I want to find arc EF. It equals the measure of the arc over 360 times it by 2, 3.14, and the radius is 7. Okay. So I went and reduced 100 over 360 down to 5 over 18. When I multiplied all this out, it came out to like 43.96, and I rounded it to 44. Hope that's okay with you guys. And I go ahead and multiply that up, and I get the measure of arc EF, or the length of arc EF, is about 12.2. Okay, so a little bit of rounding there. You know, we're kind of sticking a little bit to rounding it to the nearest tenth. I know I didn't do it back here on part A, but I hope you realize that's pi. Okay. Right, so that's use that little formula. You just got to remember it. We kind of use it for some something very similar to that for area of a sector, which we're going to kind of do next. Okay. So go down back to these next two questions, and this gets really involved. Some of you guys are really smart to probably think this one out a little bit. We're going to kind of, I'm going to do it kind of the long way, right? So I'm going to take the question here, and each end is a semicircle. So each end is a semicircle. And I'm going to do this kind of the long way, but I'm going to stop and kind of point something out. Some of you guys will get it. But let's just kind of do it this way. They tell me that the lanes of the track are 1.25 meters wide. So that's really on both sides, okay? So I'm just going to do that. They also tell me that the radius of this semicircle is 29. So it's 29. That's the radius, but each radius is 29, and that would even include this one right here. So just kind of showing you some stuff there. Then they tell me that the straightaways are 108.9 meters long. So I'm just taking the picture, I'm throwing down the stuff they're giving me, and they want to just do some math here, okay? They want to know what is the distance around lane 1. Now, some of you guys are in track, or you have to do it for PE. If I'm running around lane 1, am I running around the inside of the lane or the outside of the lane? Well, I used to have to do this a long time ago. I was taught get on the inside because it's really the shorter distance. So I'm really going to measure around lane 1 right on that line, okay? So one thing I have to do then is find the measure of this arc, okay? So we just kind of did that. Now I'm assuming that's going to be a semicircle, so I'm assuming that's 180 degrees for that arc because it's a diameter right here. Okay, I'm assuming that's a perfect circle. So I'm going to take for the measure of that arc, with the length of that arc around the inside part of that lane, it's going to be 180 over 360. I'm going to times it by the circumference of a circle. So the radius is 29, and it's by pi, okay? Okay, so take that, 180 over 360 reduces down to 1/2. 2 times 29 times pi gives me about 182.1. I believe I rounded there a little bit. And then I'm going to get that the measure of this arc is going to be about 91.1. Okay, a little bit of rounding there too. Okay. Now, I'm going to think there's some of you out there going, wait a minute, you're not being very smart there. I just want to make sure that we're still kind of using that formula. But what I did was I found this arc at this end of the track. But let's be honest with ourselves. If I took this arc down here at this end of the track and matched it up with this arc that we're working with, don't I create a circle? Okay. So technically, if I'm thinking right here, I get the circumference of a circle. Can't I just add it on now to the straightaway that we kind of listed here? okay? So what I'm going to end up having to do is take that 91.1, multiply it by 2, because I need this arc down here at this end too, because I'm running around that, and I'm going to end up getting 182, basically 0.1 where I started with again. Okay, so some of you guys were thinking about that. Some of you guys just kind of going with me. You know, each of us are going to kind of understand things a little bit differently. Okay, so once again, I'm trying to find how long I have to run around it. Now remember, if I'm running this straightaway here that I listed, I have to also run around this straightaway over here. So I've got 2 straightaways and basically a circle that I have to run around. Hopefully you're kind of understanding that. Okay. So when I take the 108.9 and I double it, because I have to run both of them, I get 217.8. I'm going to add it to the circle that I have to run around, or the two turns at each end of the track, and add that together, and it comes out to be about 400 meters. Now some of you guys that are in track know that basically tracks today are measured out at 400 meters for the inside lane. Okay. Right, for lane 2 then, you know, once again, this is lane 2 up here, but I'm going to run right on the edge of lane 1 if I'm running in lane 2, because I want to be the shortest distance. If I'm on the outside edge of that lane, I'm going to run a longer distance, and you know, I got to be fast. So around lane 2, once again, I'm going to take that 180 divided by 360, and I'm going to go ahead and find the measure of the arc, okay? But I'm going to have to change my radius now, because now I've got to add another 1.25 to how far I'm running, okay? So my radius now ends up being 30.5. I'm still multiplying it by pi, and I'm still multiplying it by 2. So remember, that's the circumference of the circle, okay? So if I do all that math, I come back, I'm still getting an arc measure here. Sorry. Of now 95.6, but I need to double that, and I'm getting about 191.5. Still running these 2 straightaways. The straightaways didn't change. They're still 108.9 meters long. I want to add that together, and I get about 405. I'm sorry, 409.3. Okay, so there's some rounding issues going on there. You might see that answer a little bit different. I think I did this one other time. It was like 407, but there was some different rounding things that we were doing. Okay, but you know, just kind of working your way through that process. Okay. All right. If we go to this example down here, is a pretty good one too. You don't have this picture, so why don't you just draw a rim? That's this piece right here. Make it a circle. You don't have to draw the whole, all the spokes and stuff. And then, but draw the tire around it. So remember, a tire is set onto a rim. Okay. And they tell me that the tire has the rim actually has a diameter of 17. So basically from the center of the rim out to where it meets the tire is 17 inches as a radius, okay? The sidewall width, so this part of the tire is called a sidewall. That has a width of 4.33, okay? So what I want to do is use that to find the circumference of the wheel. And why I need to do that, we're going to find out how many revolutions or how many times that tire is going to go around when it travels 100 feet, okay? So what we'll kind of, you know, picture in our minds, we'll find that valve, you know, where you put the air in. We'll kind of consider it on this line of the radius. But we'd use the valve, we'd mark a spot on the ground. So here's my little valve. and I know it's on the inside part, but it's just a landmark here. And I'm going to figure out how many times in 100 feet that valve is going to come down and be even with the ground again. Okay, so that's what they're asking us to do. So basically, I got to find now the circumference of this circle. Okay, so circumference is going to be 2 times pi times the radius. So I had to add 17 and 4.33, and it gets me 21.33 as the radius of that whole thing put together. Okay, so I'm going to go ahead and multiply all that up. And you know, for me and my being an old guy, I would have doubled the 21.33 and got the diameter and then multiplied that to pi. So that's how I used to have to do that. But anyways, we get a circumference of 134, but it's in inches. And the problem is that I've got my circumference in inches, but they're asking me how many times does it roll in 100 feet. And so kind of 2 ways you could do this. I just took 100 and I multiplied it by 12 inches and I got 1200 inches. Okay, that's just me. You could have converted this 134, I could have divided it by 12, and I forget what I got here. I get I don't know, like 11 point something or whatever. Okay, I forget. So what I'm going to do is I converted that to 1200. I'm going to take the 1200 and divide it by 134. And it comes out to be about 8.95 revolutions. And so I just rounded it to 9. So that valve, no, the valve's not hitting the ground, but it's just a landmark on the tire. That valve is going to, when I roll the wheel, it's going to hit the ground that many times, or hit a spot above the ground that many times in 100 feet. Okay.